Steel is a costly material, and as an engineer, we always try to reduce the steel usage in any structure. Well, not by compromising with the structural stability. One way is to use the steel optimization routine available in STAAD, which finds out the most economic section required to resist the applied load. But this is not the only solution. Optimization does not mean use of an economic section only. Rather, we need to ensure proper distribution of material where it is required. And with this approach, we can further reduce the steel quantity and overall construction cost of any structure. Hi, my name is Surajit Ghosh, and in this video, I will discuss about two methods which can not only reduce the steel usage but also provide several other advantages over conventional design. First one is optimization using castellated or cellular beam in place of general wide flange or plate girder section. And second method of optimization is by using tapered member, which is very common. In any PEB structure, tapered sections are used as a column or beam member. Today, I'll cover the basics of castellated and cellular beam and discuss why these sections provide more economic design results. In the next part, optimization using tapered members will be covered. By the way, this is the sixth part of steel optimization series, and if you really want to know about optimization, you can go through the last 5 parts where I have discussed about conventional optimization process available in STAAD. Consider these three structures. First one is an auditorium or stadium roof structure. Second one is a MRT station building, and third one is a large warehouse building. These structures are completely different from structural point of view as well as from their purpose. But there is one similarity. Each of these structures require a large unobstructed space. There should not be any intermediate column or supports which can restrict the viewing angle or any movement. If we want to design the roof structure, then it is not possible to include any intermediate supports, and all these large span beams must have the capacity to resist all gravity and lateral loads and satisfies the serviceability criteria. And here comes the problem. Scenario 1. For this PEB structure, there are multiple interconnected bays in the longitudinal direction, and we can easily introduce cross bracing to stabilize the structure. But in the transverse direction, the entire span is unsupported, and all loads from roof are transferred to these large span members. This results in large deflection. We know that maximum deflection is proportionate to the span length. It's L cube. So if the span length increase, though the applied load is same, still the deflection value increase. To minimize this deflection or to satisfy the serviceability criteria, we need to assign a section with higher depth. That's why for large span, steel usage is higher. Scenario 2. This is a composite deck of a steel building, and due to higher floor load generated from the dead and live load, the bending moment in the floor beam about major axis is quite high. We know that this moment is resisted by the flange of the beam, right? If we look at the bending stress diagram, we can easily conclude that the contribution of the web in resisting moment is very low. Majority portion is resisted by the flange alone, and if we increase the distance between the flange or the lever arm by increasing the overall depth of the section, moment capacity also increase. That's why to resist higher bending moment, section with higher depth is required, which eventually increase the steel usage. From these two examples, it is clear that we need to assign a section with higher depth if the span length is large or if the bending moment about major axis is considerably high. But there is one problem. This section is not utilized properly. With the increase of overall depth of the section, shear capacity is also increased, right? But if the section is not subjected to high shear, this extra wave depth or higher shear capacity is of no use. Now the question is how we can optimize this section so that this unutilized wave portion is reduced without affecting the bending capacity. And that is the basic concept of castellated or cellular beam, where we reduce steel from the wave without decreasing the depth by introducing wave cutouts. Before going into the technical details, I want to cover how these sections are manufactured. And that is very interesting. By the way, castellated and cellular beams are technically same. There is not much difference except the hole type. For castellated beam, the holes are hexagonal, and for cellular beam, the holes are circular. Also, beams with several other shapes of hole are manufactured like elliptical or rectangular hole, depending on the side requirements. In this video, I'll focus only on beams with hexagonal and circular holes. Why these beams are more economic and more suitable as a long span rafter or floor beam? Answer to this question is hidden in the manufacturing process. Do you know these cellular beams are manufactured from normal hot rolled sections? The process involves cutting and welding. For castellated beams, first a hot rolled section is cut along the length in two pieces in proper pattern. This cutting is normally performed using a computerized equipment with trained professionals either in site or in fabrication shops. As you can see, the wave of the section is cut in proper pattern and then these pieces are separated. Next step, arrange these sections in such a way that the pattern match and then both of these pieces are welded together. What this produce? A section with higher depth with holes in the wave portion. There are some excess portions at both ends which are then removed. That is the only wastage in this whole castellation process. Similarly, for cellular beams, the wave portion is cut twice as a semicircle in such a way that these form a complete circular hole. Then these two pieces are arranged properly and welded to create the cellular beam with circular hole in the wave. For cellular beam, the overall wastage is higher than the castellated beam. But it also provides few great advantages which I will discuss later. Also, we can create a section with higher depth by inserting an additional plate during welding. These sections are fully customizable. Depth and shape of the hole can be altered as per requirement without using any additional steel. And if required, we can also manufacture asymmetric section with higher bottom flange by joining two separate sections. These cellular beams are created from a hot rolled section and final product has higher depth than the initial section. Normally, cellular beam has 50% higher depth than the initial section, which means the bending capacity of the cellular beam is much higher with less deflection than the initial section without even using any additional steel. We just take a normal wide flange section, which is not adequate, and then distribute the steel in such a way that the final section has 30 to 35% more capacity than the initial section. For an example, if a wide flange section with 600 mm depth is required, then we can easily use a 400 mm section by converting it to a 600 mm cellular beam with same results. Just imagine how much cost you can save with this approach. To elaborate this, I have created this FEM model in STAAD Physical Modeler. 3 I sections with 12 meter span length are modeled with plate mesh. For more details on this mesh generation, you can go through my previous series on finite element meshing. These 3 sections have same flange width and thickness, but overall depth is different. This section has a depth of 400 mm. Depth of second section is 600 mm, and depth of the final section, which is a cellular beam, is also 600 mm. You can easily notice that the mesh around the holes are properly generated, as I am using physical object approach. Assume that this cellular beam is generated from the first I section. I section with 400 mm depth is divided in 2 pieces, and then these sections are welded together. It increased the depth of the section by around 50%. So section 1 and 3 has same weight, same steel usage. What happens when these beams are supported on 2 piers and then 2 point loads are applied on these members? To find this answer, I have analyzed the model and then from the post-processing deflection table, check the analysis results. Maximum midspan deflection in vertical direction of the first section is 1.642 mm. Second section is 0.814 mm. And cellular beam is 0.888 mm. Deflection of the cellular beam is considerably small than the initial 400 mm section, which is very logical. As we have increased the depth of the section, deflection value is also reduced. And if we compare the deflection of the cellular beam with the same depth hot rolled section, it is very close. This suggests we can easily decrease the deflection value without going for a larger section, just by changing a smaller section to a castellated or cellular beam. I am unable to show you the comparison of bending capacity of these beams, but you can easily understand that the bending capacity of the cellular beam is same as the hot rolled section with 600 mm depth, and obviously this value is far greater than the capacity of 400 mm section. So, if we want to reduce the deflection of a long span beam or increase the bending capacity to resist higher moment, there are 2 solutions. Either we can select a hot rolled section with higher depth or go for a cellular beam. If we compare the cost of these sections, hot rolled section with higher depth will obviously cost more. For cellular beam, there are some additional costs for fabrication, cutting and welding, and also there are some wastage. But overall cost of the section is always less than the same depth hot rolled section. It has been observed if the span length is between 40 to 120 feet, then castellated or cellular beams are most ideal and economic section. This is only a comparison based on the steel usage. There are several other benefits. Do you know we can decrease the floor-to-floor height by using cellular beam? For any warehouse or building structure, there are several utility lines, pipes, ducts, which spans along the entire floor from one side to another. When hot rolled sections are used as a beam, these pipes are normally placed under the beam using separate rack or tie supports, and to accommodate these pipes without affecting the clear distance, we need to increase the floor-to-floor height. When cellular beams are used as a floor beam, this additional space under the beam is not required. For cellular beam, there are multiple holes within the web, and we can easily accommodate all these utility lines through the web holes. If required, we can customize the holes or join 2 holes to fit a larger pipe. Obviously, an additional web stiffener plate at this location is required. Reduction of the floor-to-floor height of a multi-story building also reduce the overall construction cost. There is another major benefit. We can easily design a large span with cellular beam without any intermediate column. For any building with composite deck floor, it is extremely useful as we can design a very large unobstructed floor. Consider this floor panel with total transverse length of 60 feet. As the total span length is high, deflection and moment values are also very high. If we use hot rolled section as a floor beam, then either we have to provide columns at intermediate level to reduce the deflection, or we have to use wide flange section with higher depth. In such case, if we use cellular beam in the transverse direction, these beams can easily reduce the deflection and also provide larger bending resistance. So we can remove the intermediate columns and provide cellular beam in the transverse direction along with wide flange section in the longitudinal direction. With this, we can reduce the cost in three aspects. We are not using higher section, and as the steel usage of cellular beam is similar to a smaller depth section, material cost is reduced. We have also removed a row of columns which further reduce the overall structural cost, not only for the column, but also additional cost of the foundation will be eliminated. Finally, as there are less number of joints, we can further reduce the cost of connections. That's why for any composite deck structure, cellular beam is a perfect choice and widely used. There are so many other benefits which I am unable to cover in this video. For example, we know that arch type beams provide additional advantage over straight profile or truss, and that's why in any large stadium or station building, arch beams are used in the roof. For castellated beams, it is very easy to bend the cut pieces first and then weld it together as an arch. Bending a wide flange section is rather tough, so castellated beams are preferable for any arch type roof. I am not sure whether you have used these types of castellated or cellular beams in any of your project, but these are widely used in several sectors. Note that these sections are not good for axial force or high shear as we are deliberately weakening the web. Not only that, due to cutting and welding, there are more residual stress than the normal wide flange section. We need to perform several additional checks, including checks for shear and tear of the welding for the safety of the member. AISC Design Guide 31 is the most detailed design code on castellated and cellular beam design. In this code, 8 additional checks are recommended for any castellated or cellular beam. I am not going to cover the design philosophy in this video. If you need any information on the design basis, let me know in the comments. In STAAD, AISC AST 1989 code is available which can perform castellated beam design. Also, we can assign symmetric castellated sections which is available under US rolled steel database. Note that design is performed only for moment about major axis and shear along the web. If there is any axial force, torsion, MY or FZ force components, then design will not be performed. And if you want to design using any other code, it is not possible at this moment. It is also not possible to assign any custom castellated or cellular beam in STAAD as the section profile change along the length. There is no option available in STAAD to handle this. Better to model this type of member using FEM for analysis. The best product which can handle castellated or cellular beam design is RAM Structural. Do you know RAM structural is very good for composite deck design, and we can easily assign any castellated section as a floor beam. Several standard databases are available for castellated and cellular beam. We can further customize the section or holes as per our requirement and design using the latest AISC code. I'll cover this later. That's all. In this video, I have discussed about an optimization method using which we can distribute steel over the cross section so that the section is fully utilized. In the next video, I'll talk about another optimization technique where we will distribute the material along the length of the member using tapered member. Stay tuned and thanks for watching.